Hey folks, for this screencast, we're going to talk about something called the Gauss-Newton method, which is a form of nonlinear regression, and it's two methods put together. So I have some Python code that I've already started, and by the way, if you're trying to download this Python code when you're watching this YouTube video, if you go to my GitHub, my Python repo, there's a folder called opt and then Gauss-Newton. I decided to do this in Python because everybody in my university has switched over to Python. So I just want to kind of guide you through exactly what's happening here. So the Gauss-Newton method is two methods put together. So Gauss's method is a form of linear regression where you have a data set that you're trying to fit, and typically it's linear, and so you have n equations that you have n data points, and you're basically trying to fit one line through it. And a line only needs two coefficients. It needs a slope and an intercept, or depending on point slope form or whatever. And you can put it into this form where y is all of your y data points. You have this matrix A, which is a matrix of your unknowns, and then this matrix H, which is kind of a form of your equation really. And I have a YouTube video that kind of walks through least squares regression, but at the end of the day, you end up having to do this left pseudo inverse in order to solve this equation because you have more equations than unknowns. Now Newton's method works really well because it's iterative, but when you expand Newton-Raphson to 2 dimensions, your Jacobian is only easily invertible if it's a square matrix. Well, if you're doing least squares regression, your H matrix, which sort of relates your data to your coefficients, is not square. And so you end up having to figure out, like, how do I do a left pseudo inverse for Newton's method? And that's basically where the Gauss-Newton method comes in. And so if you run over to Wikipedia and you look at the Gauss-Newton method, you can kind of see where that comes together, where you have the iterative process of Newton-Raphson, but you also have the least squares regression component over here on the right. And so we are going to do this Gauss-Newton method for this example problem that one of my students sent me, where we're trying to fit this equation here, where A naught is an unknown, A1 is an unknown, and here's the data here that we're trying to solve. The Jacobian is the partial derivatives for A0 and A1, and that's already here, so that we can just throw that in no problem and then basically plug it into this algorithm here and solve, and we should be able to move through it pretty quickly. So the first thing that we want to do is create a function where if I give it A0 and A1, it will return, well, A0, A1, and I guess X, it will return the values of Y. And so I'm going to call this def f, and I'm going to say I'm going to give it A0, I'm going to give it A1. Actually, I'm just going to give it A, and A is just going to be a vector. And then I'm also going to give it X. And so I'm going to say A0 is A of 0, and then A1 is A of 1. And then the function that's evaluated, we need to go over to the appropriate tab, is going to be A0 times 1 minus. So we'll say A0 times 1 minus NP EXP negative A1 times X, and we'll call that Y, and then we'll go ahead and return Y. Now there's a couple things that we need to do to make this work. First, we need to import NumPy as NP. I'm assuming that we are going to plot, so I'm going to go ahead and import matplotlib.pyplot as PLT. And I'm also going to import scipy.linalg as S, because I am assuming that we are going to need to do an inverse, just judging by Newton-Raphson's Jacobian. Okay, so now we need to do what? Well, we need to establish an initial guess. So first, I'm going to put modules up here, and then I'm going to say functions over here. And then down here, I'm going to say, initial guess. Okay, so my initial guess for A is going to be 1, 1. And the reason why I do that is because that is what the book says. Okay. Now, the next thing that I want to do is I want to evaluate the function from the first and the last data point. So I want to go ahead and create my data set too. So I want to create my data set. Okay. And so I'm going to say x data is np.array, and then I just need to copy this over, 0.25, 0.75, 1.25, 1.75, and then 2.25. Okay. Then I'm going to have my y data is np.array, and I'm going to do 0.28, 0.57, 0.68, 0.74, and SciPy went crazy, or not SciPy, and then 0.79. Spider went crazy a little bit. Okay, now before I actually do the initial guess, I actually kind of want to jump down here, and I actually want to, plot my function. And so I'm going to drop a figure. I'm going to drop a plot for x data and y data, and I'm going to do blue stars. I'm going to go ahead and throw a label in there and call it data. I'm going to do not a plot, I'm going to include a legend. I'm going to include what do I want to include? I want to include an x label where this is x on the x-axis, plt.y label is y on the y-axis, plt.grid, and go ahead and plt.show. And if I hit F5, it says invalid syntax. I'm confusing MATLAB for everything, so it just kind of freaked out. And then there you have it. So there's my data set, right? And so when I make my initial guess, I want to make my initial x vector. So you see here, I have to give it a and x. I'm going to make a linspace. Oof. So there's a couple things. So I could make an x be, yeah, that's fine. So when we're evaluating the function, when we want to plot it, we'll use the x that has a linspace, so it has a lot of data points. But when we're doing the iteration, we actually just want to use the x data. So this is just fine. Okay, so let's look at the Gauss-Newton method, right? So we're going to need to have our iterations, so that's fine. There shouldn't be an issue there. We are going to need to make our Jacobian here, and so we're going to need to make a def j. And in order to get j to work, if you look at the Jacobian, you'll see that the first column is 1 minus e to the negative a1x, but x is a vector, so that's going to be a column. And then you're going to have a0, the partial derivative of f with respect to a1. So this is going to be basically 5 rows and 2 columns. And so what do I need to get this to work? I need to give it a, and I also need to give it x. And so I'm trying to think if I can do this with Python. I basically want to make, I'm going to have to do like horizontal concatenation and things like that. I could do a for loop, and it'd be nice if I could just vectorize this, because that's what MATLAB does. Let's see if I can put these two matrices together. So I'm going to say df da0, right, is equal to 1 minus np.exp of negative a1 times x. So x is an input, a1 is a of 1, and then a0 is a of 0. Okay, so there's df da0. Then I'm going to say df da1 is a0 times x, a0 times x times np.exp, and it keeps trying to autocomplete, and then I can't see negative a1 times x. Okay, and then what I want to do is I want to concatenate those two together. So I think it's going to be return np dot vcat. Is it h concatenate? I'm going to pause and see if I can figure this out. Okay, apparently it's called vstack, and you give it the two vectors that you want to concatenate. So we're going to do df da0 and df da1. We're going to test all of this, okay? So basically, eventually we're going to put a while loop in here. But for now, let's just compute everything, okay? So in order to get the equation to work, we've got to get our Jacobian. Okay, so let's see if we can get our Jacobian to work. So I'm going to say ji, right, the current iteration is going to be, and I'm going to call this ai, is going to be jai and then x data. So x data is never going to change. Then I'm going to go ahead and print ji just to see if that actually worked. So it made, yeah, so it thinks I need it to be, like if I type in print np.shape of ji, right? It's a 2 by 5, which I don't want. I want a 5 by 2. So maybe if I just return np.transpose, like that. Yeah, see now it's a 5 by 2. And that should be good to go. I kind of want to print dfda0 here, just to make sure. So yeah, so this is dfda0, which is 0.22. And so that means this first column is dfda0 and this second column is dfda1. Okay, so the partial derivatives are working properly and we're computing our Jacobian properly, so that's all good there, okay? After we get J, we've got to do J transpose J inverse. So let's see if we can get that to work. So we're going to have J transpose J is equal to np dot transpose of Ji, and then we need to do np dot matmul, because this is Python, and throw a Ji in there and see if that doesn't freak out. And it doesn't. I'm also going to go ahead and turn off. Oh wow, I have all of my figures just like open. There's got to be a way. Isn't there like a plt.close all here, I think? Yeah, there is. Okay. But let's get rid of the show. I'm tired. I kind of don't want to see this figure. Actually, we can do a block comment. Those are pretty slick. Okay. So there's a block comment right there. And so let's go ahead and over here type in J transpose J. So a 5 by 2, so this should be a 2 by 2, right? Yeah, and it is. Okay, cool. So that makes sense because we only have 2 unknowns. So now we've got to invert this matrix. So J transpose J inverse is going to be np.linalg. So I guess I don't actually need scipy. I forgot. Because there's a linalg function. I'm going to do np.linalg. Is it inverse? Yeah, and J transpose J. And give me a good on that. So J transpose J inverse. So if I do np.matmul of J transpose J inverse, comma J transpose J, I should just get the identity matrix. And I basically do. I get 1 on the diagonal and basically 10 to the minus 17. Okay, so my inverses are working properly. So now I've got to do J transpose J inverse J transpose. So I'm going to do J transpose J. I'm going to just put a 1 for inverse. J transpose is going to be np.matmul of J transpose J inverse times J transpose, which is np.transpose of Ji, and that should work. Module has no, I just did it up here. Did I spell it wrong? I spelled it wrong. Okay, so there's the first part. Now we need this residuals thing. Okay, so what are the residuals? What you need to do for the residuals are, you need to say residuals, you need to give it a, and I think you can just give it x, which is fine. And then basically what you do is you need to compute, no, you also need to give it the x data and the y coordinates. Yeah, this is kind of confusing. So how do I want to name this? You want to give it the x data points and the y data points. Let's do that. And then basically what you do is you say, first, to compute what y is for the values of a. So y is equal to f of a comma x data, right? So that will give you the data points. So that will give you, for a certain value of a0 and a1, it will plug it into the function and give you those, like where those variables are. And then your delta is y minus y data. And then your residuals, I'm going to return. Ooh, is it a scalar? No, I think it's just delta squared. I think you just square everything. And so my residuals is just residuals of a comma x data comma y data. Let's run that and see what happens. A is not defined. That's because it's AI. So let's type in R here. Yeah, so there's our residuals, which is a 5 by 1. That makes sense. And we should be able to multiply everything. Actually, and I want to do transpose again. So I'm going to do np dot. You know what? Man, it's too late. I was going to say, I wonder if, I made my arrays rows. I wonder if I would have just made my arrays columns and got rid of all the transposes, but I already have the transposes in there, so I don't really want to like mess with it. Okay, so if we do J transpose J inverse, J transpose times the residuals, we should get a 2 by 1. So I'm going to say, what do they call this thing? I'm going to call this step. My step is the J transpose J inverse, J transpose, oops, and I'm going to do a matmul times R and see if that doesn't freak out, and it doesn't. And step is a 2 by 1. Fan-freaking-tastic. The question is, though, did I get the same answer as them, right? Okay, so there's the Jacobian, 0.2, so let's type their Jacobian in, JI, sorry. So they got 0.22, 0.52, 0.89 at the bottom, and they got 0.237, cool. And then there's their J transpose J. So if I do J transpose J, they got 2.3, 0.94, 0.44, that's right. And then J transpose A inverse, 3.64, negative 7.8, that looks good. And then they do some weird things, and then they get negative 0.15. So what did we get? Not for R, sorry. What did we get for our step? We got 0.015. So I think there's another page. Yeah. They got negative 0.27. So we got something different than them. Oh, wait, no, there we go. There's 0.27. Wait. Oh, and 0.501. So yeah, so I got something different, but before we debug, let's just try this and see what happens. So, because they add, I'm subtracting. I'd be curious to see if, yeah, let's just try it. So anyway, so I'm going to say AI is now equal to AI minus the step, and I'm going to hit F5. And so now AI should be different than what we started with. Yeah. And what is the answer? A0 is 0.79 and A1 is 1.6. Okay. So then at the end of the day, now I actually do want to plot this, PLT, and I want to get rid of this block comment. And now instead of plotting the Y data, I want to evaluate, and this is where I'm going to make, so I'm going to evaluate the solution, right? So I'm going to make x equal np.linspace from the minimum value of my x data to the maximum value of my x data. And I'm going to give myself, say, 100 points. And then my y is going to be my function evaluated at ai comma x. Not the x data, but x this time. And then I'm going to plot my x comma my y in red stars, and I'm going to make a label. It would be nice if Spider didn't like try to autocomplete, because I can't see when it does that. Maybe I'll try to turn that off in a future video. Or if you know, post in the comments and let me know. Anyway, so this is going to be my fitted, I'm going to say least squares regression. Nonlinear least squares regression. And let's see what we got. Okay, so that is... You know what would be cool too is if we had a cost function. So these are our residuals, right? So def cost of a comma x data comma y data is basically the return, the np dot sum of the residuals of a comma x data comma y data. And so if I did my initial guess and my initial cost, that would be cost of AI comma x data comma y data. And what I could do is I could print initial cost equals cost I, right? And then, after every solution I can say, current cost equals cost I. And then I could just do the exact same thing. Cost I is cost of AI comma x data y data. And it'd be cool to see if in that one iteration it went down. And so, okay, so even though I didn't get the same answer as the book, the cost is going down. And what's interesting is that if you go back to the book problem, it did say, you know, I think back over here, it said that the initial cost was 0.0248, and that's exactly what I got, 0.0248. And what's interesting is that after their first iteration, their cost goes down to 0.0242. My cost actually went down more. So yeah, I guess I don't know what they're doing in the book, but let's just see if this works, because I grabbed the Gauss-Newton method from Wikipedia, and I feel like Wikipedia is doing a pretty good job. Okay, so let's loop this now, or maybe not. Maybe just for it, for I in range 0 to 100. Let's just loop this 100 times. Okay, and let's just see what happens. I'm just gonna run this, and you end up getting a singular matrix. So this is interesting, right? So the cost goes down, and it keeps going down, and then it goes back up. And so this is kind of interesting. So then it blows up here. So this is why I really like the Levenberg-Marquardt process, where you add an alpha parameter in here. And so I like to sort of tune that alpha parameter and say, you know what? Don't go too fast. So that was too slow. That alpha parameter was too much. So let's try 0.1. Oh wait, I made it 0. Okay, we're getting somewhere. So maybe let's do, instead of 100 iterations, let's do 1,000. Yeah, so then it just went to a nan. Okay, let's pause this. Okay, I do have an idea. What we could do is we could start alpha at 1.0, right? I don't remember where I learned this method, but basically you say while alpha is greater than 0.01, right? And what you do is you create an A next, right? And then you evaluate the cost, right, at A next. And then you say, if cost next is less than cost I, everything's fine. But if cost next is greater than cost I, you divide alpha by 2, right? So you say alpha equals alpha divided by 2.0, right? And then otherwise, if that's not true, you say cost I is cost next, and AI is A next. And then you print the current cost. Otherwise, you say print alpha equals alpha. Somewhere in here, my computer is freaking out. Yeah, so there you go. So basically, like, cost is getting smaller, and then it just makes it gets to a point where it can't converge. What is my solution? So I'm going to print solution equals A, right? AI. What do I end up getting? 0.94 and 1.03, and what do they get? .79 and 1.675. Yeah, I'm nowhere close to that. It's like we hit a local minimum, you know? What if you go for gold and make alpha 10? Yeah, it's like there's a local minimum, and you like jump over it. Because their cost at the end of the day, when they're done, they get 0.000662. They get like a ridiculously good answer. Maybe let alpha get even smaller. mean, it's close. And then what's my, here, let's do this. Let's print my residuals. Print residuals equals what? A comma X data comma Y data. So you give it residuals. No, you want cost. Cost is AI comma X data comma Y data. Well, I guess that pop-up came in handy. Yeah, so my cost is 0.01. No, not residuals. Cost. It's 0.01. And they got 0.000662. I have a question. I'm going to make this my initial guess, 0.79. Let me see if I can at least get the same answer as them. So my initial guess is going to be 0.79 and then 1.6751. So if I run that, yeah, I basically, okay. So they definitely converge on, I mean, depending on what your initial guess is, the answer that they got in the book is definitely right. But I'm running into like horrible local minimum problems. Great. Okay, folks, I figured out the issue. So when I was computing R, the residuals, I was squaring it here. When I was computing the Y minus the Y data, I was squaring it. And so the reason why you need to have the sign is because Newton-Raphson needs to know which direction to go. And so basically, since I was squaring it, it just turned the whole thing into a bowl. And so Newton-Raphson just always picked the positive route. So it was falling into a local minimum because it wasn't following the steepest descent. And so I added a bunch of print statements. I'm going to go ahead and just get rid of those. But now I don't even need this alpha parameter really. The solution. Okay, I guess I actually kind of do. So the solution converges pretty well, but it even it halves the alpha parameter a little bit. So adding that in was kind of nice. But I actually got the solution that they did, 0.719. Let's see. Yeah, 0.71986. And then 1.6751. Yeah, so I got it. So yeah, I guess I'll go through the code one more time just so that we're kind of all in cahoots. And so basically, you got Gauss's method in comments here, just showing the linear regression. Newton's method which is iterative, importing all the modules. Here's the function that we're trying to evaluate. The residuals, which is actually just the fit minus the data to preserve the sign. That way you know it's positive or negative. The cost function, which is the residuals squared, and then you add them all together. And then you've got the Jacobian, which is the partial derivatives that I v-stacked together. Then you've got the x data and the y data. Then I've got my initial guess, my cost function. I have this alpha parameter that I added in there that I don't really need, but I put it in there anyway. I compute my Jacobian, then I do J transpose J, compute the inverse of that, multiply that by J transpose, compute the residuals where I just do Y minus Y data and preserve the sign. Then my step is from the equation from Wikipedia, which is this nastiness here, J transpose J inverse J transpose times the residual. And then I compute A next, which is AI minus alpha times step. Alpha is 1 in the beginning, so it's basically just the same equation from Google. And then I compute the cost just to make sure if the cost goes up, I divide the alpha by 2, and then I print alpha so I know what's going on. And then if it's not, if the cost went down, I save that as the next iteration and then compute the cost. And then once the thing breaks out, once alpha gets too small, which happens pretty quickly, I then print the solution, AI, the cost that I got to, I create a lint space vector, I evaluate that function, and then I plot that and the data set, and you end up getting this nice pretty plot. So that was way longer than I thought. I am sorry for making a 30-minute video. If you're still here, congratulations. Again, this code will be on Python opt Gauss-Newton. I hope that you have some happy coding, and I'll see you in the next video, whenever that will be. I haven't really been making very many videos, but it is what it is.